Hot Moses, the seawater membrane carbon sequestration startup. Caused by the elevated concentration of CO2, the climate change calls for urgent carbon capture. Direct ocean capture has higher potential to contribute as the ocean holds 50 times more carbon content than the atmosphere. Our company strives to address limitations in separation technology to enhance the feasibility of direct ocean capture.
Our proposed process uses bipolar membrane electrodialysis, abbreviated to BPMED, to create an electrochemical pH swing in seawater. Taking in seawater from the nearby ocean surrounding Beaumont, Texas, our location chosen for its wave strength, favorable tax laws, and proximity to already constructed carbon pipelines, and ran through a particle filtration system to remove large debris. Then, 0.5% of bulk flow is fed through a water softener to remove hard minerals like calcium and magnesium. This softened flow is then sent into the membrane stack of alternating cation-anion exchange membranes, which enable water to preferentially dissociate into H plus and OH minus ions, which then move into acid and base streams. The acid stream is then contacted with the other 99.5% of bulk flow seawater to lower its pH. Natural seawater contains carbon primarily as carbonate and bicarbonate rather than free dissolved CO2. At sufficiently low pH, about 4, much of the inorganic carbon becomes dissolved CO2, which allows for easier separation. The dissolved CO2-rich acid stream then enters a flash evaporator, where like a soda can popping, pressure is released, and CO2 rushes to the gas phase to be removed. The base stream generated by the membrane stack is then recombined with the treated seawater. This neutralizes the acidified water and restores alkalinity, allowing the CO2-depleted effluent to gradually re-equilibrate with the atmosphere, drawing carbon from the air into the ocean. Improving on the incumbent technology, which is a California-based startup called Captura, Moses increases the rate of CO2 effluent equilibration using spray nozzle emitters to increase the contact area of the CO2-depleted seawater effluent stream to the relatively rich CO2 in the air. We also had a competitive advantage by tapping into Texas's robust network of carbon pipelines.
Key advantages include environmental benefit by reducing atmospheric and oceanic CO2 and only using renewable energy, massive scale potential with ocean holding 50 times more CO2 than the atmosphere, and leveraging natural equilibrium by removing CO2 from the seawater. This will cause more CO2 to be pulled from the atmosphere into the ocean. Key risks include environmental risks by disrupting marine ecosystems and affecting organisms sensitive to pH, as well as chemical and electrical handling hazards.
The existing direct ocean capture startup Captura reports 90% removal of carbon dioxide after acidification by bipolar membrane electrodialysis. We use this efficiency as a basis for our calculations. We aim to remove 100 tons of carbon dioxide per year and assumed all energy would be generated from renewable resources such as wind and solar to minimize our carbon footprint and energy costs. We did a mass balance on carbon dioxide using reported data on dissolved inorganic carbon in surface seawater and found that we would need to process approximately 13,000 kilograms of seawater per kilogram of carbon dioxide removed. We then did an energy balance on the bipolar membrane electrodialysis process and subsequent flash evaporation, and found that our process would require 1.66 kilowatt hours of energy per kilogram of carbon dioxide removed. We used the mass and energy balances to calculate our operating expenses, assuming average renewable energy costs, and estimated our capital expenses based on current cost of the equipment needed for our pilot plant. We performed a simplified levelized cost of production calculation using standard assumptions and found our levelized cost of production to be 20 cents per kilogram carbon dioxide removed.
Here, we calculated the membrane area needed to have the performance of 100 tons per year of CO2 capture with 90% target conversion. Using Faraday's law and water carbonate equilibrium, we estimate 2.6 square meter of membrane needed to which is much better performance than our competitors.
And last but not least, we performed a sensitivity analysis, as seen on this slide. Our sensitivity analysis assumes a simplified first-order model where key performance parameters such as CO2 flux per membrane area and energy consumption per ton captured remain constant across all operating scales. As a result, both membrane area and NPV scale linearly with target CO2 capture, reflecting an idealized system without efficiency losses or scale-dependent constraints. In reality, factors such as increased electrical resistance at higher current densities, mass transfer limitations in the stripping unit, and membrane fouling would introduce nonlinear behavior and likely reduce performance at larger scales. Therefore, while this model is useful for establishing a baseline feasibility and understanding primary drivers, future work should incorporate these second-order effects to better approximate real-world system performance. And here are our references. Thanks!